Okay, so we are starting the part 2 of AP Chemistry Unit 5 lecture. We're going to just pick up where part 1 left off. So let's begin with factors that are affecting solubility. Right here. So formation of a liquid solution begins by separating the solute into its individual components. So if you guys remember the sodium chloride example that we had, so we would have this sodium particle, it's positively charged, chlorine particle, negatively charged, and the lattice would just simply be an alternating solid formation. It's called crystal lattice. Again, here's another sodium, here's another crystal, chlorine, and here's the bond that these guys make. And it's only the opposites attract, right? So sodium is bonding with chlorine, and chlorine then in turn bond with the positive sodium ions that are around it. So this is called crystal lattice. Some of you guys may be familiar with this term. Okay, so formation of liquid solution essentially begins when you break these bonds and you're cutting these apart so that ultimately you're separating the sodium ions and chlorine ions. So this is in a cup. Let's say we're dissolving in water. You end up having these separated ions that are floating around. What is happening when you break down these molecular force is that you're actually overcoming what we know to be intermolecular forces. And we're making room for the solute. So when there's a solute-solvent interaction in a given reaction vessel, so we're going to say a glass of water, then you form a solution. So in this case, we formed an aqueous salt solution. I'll try to write straight. Great. Now let's go to the next page. Alright, so the rule of thumb for dealing with solubility when it comes to solutions is that we use this phrase that says like dissolves like. It's supposed to be an arrow again. Solubility is favored if the solute, again, solute is something that is getting dissolved, and solvent, this guy, is doing the dissolving. Great. So what that means is that if the solute has a similar characteristic, that means similar for me, characteristic as a solvent, then it would dissolve very well. What that means is, an example with that, it would be if you have a polar solution or a polar solute that is interacting with polar solvent, then it's going to be definitely soluble because polar components of solute likes to react with solvent, polar solvent. On the other hand, if you have a nonpolar solute interacting with polar solute, then it's immiscible, meaning that it does not dissolve. Nonpolar, of course, bonding with or interacting with nonpolar substance is definitely going to be dissolvable. So the word miscible means that it's dissolvable, so it's soluble. So word miscible is same thing as soluble. So easy way to think that is nonpolar dissolves nonpolar, Polar dissolves polar. So this is a good time to review what makes something polar. It's very important for you to be able to distinguish or determine how a compound becomes polar or non-polar. And this is a rule of thumb that we want to focus on here. Great. Alright, let's move to the next page. Okay, so I want you to go ahead and discuss the solubility of each of the following solute in carbon tetrachloride. Ammonium nitrate, 1-pentanol, and 1-pentane. Or just pentane. Explain why each solute will or will not dissolve. Now this is where I'm going to pause and let you guys work on your own and discuss the solubility characteristic of these molecules. Okay, so coming back to this, I'm guessing that many of you guys did not know what ammonium nitrate and 1-pentanol and 1-pentane look like. Well, the good thing about one good thing about having an online lecture is that you guys can actually use the internet to look these structures up. So ammonium nitrate, if you look it up on the internet, oh, let me choose a darker color, looks something like this. Here's an oxygen coming from nitrogen with 2 oxygens, and these guys have a negative charge attached to it, and then you have floating ammonium charge, ammonium that's floating around with ammonium nitrate. So that's your ammonium nitrate. How on earth are you supposed to be able to tell whether this guy is going to be dissolved in carbon tetrachloride? Well, let's talk about solubility rule that we just talked about, right? The characteristic of solubility. Carbon tetrachloride, I'm going to draw over here, has carbon with 4 chlorines attached to it. Now, I'm not drawing the extra lone pairs because it's assumed to have an octet, right? So looking at this, would you say that this is polar or non-polar? Yeah, it's definitely non-polar. This is a non-polar molecule because you have a dipole moment pointing toward all the Cls, and when you have that, they essentially cancel each other out. So there's no overall dipole moment. It's completely canceled out. So there is no effective dipole moment. So this is a good time to review that concept as well. Dipole moment. Okay, so looking at this molecule, would you guess that it's a polar or a non-polar compound? I would guess that it's a polar compound because of all these charges, right? So we can see that there is an unequal distribution of negative and positive charges overall in this compound, in this component in each of the components. So, and here's another positive charge coming from nitrogen. So I'm going to assume that this is polar, and that's actually the correct assumption to make. So when you have a polar compound mixing with the non-polar compound, this is a CCl4, what would you assume there to be? A completely soluble product, or another word, immiscible product? So the fact that it's combining polar and non-polar says that it's actually not going to be soluble. So we say that the product of carbon tetrachloride and ammonium nitrate is going to be immiscible. Great. So how about pentanol? I'm sure by now you guys looked up what pentanol looked like, and we know that it looks something like this. Here's carbon, another carbon, 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 with an OH attached to it. Now, these carbons are assumed to have hydrogens. I know it's a little too much organic chemistry for you right now, but it doesn't really matter because all you're looking at is just overall structure. So, here it is. When you look at it, you realize that the O and H, there's got to be these 2 lone pairs coming out of oxygen. How do I know that? It's just like water, where in water, you have these guys, right? And you always know that there's going to be these 2 lone pairs. So whenever you see an OH for this particular area, sorry about that, this particular area, and you see one side of oxygen bonded to something else, there's tends to be a lone pair attached to that. Okay, I'm going to take a quick pause. Okay, so picking it back up, sorry about that. OH, you assume that there's a lone pairs, right? So if there are lone pairs, there tend to be an unequal charge distribution. So there's more pull toward, in terms of dipole moment, toward a more negative, electronegative oxygen. So there's an overall dipole moment that's pulling the rest of this molecule toward this oxygen. So this molecule is therefore polar. So again, we have a polar molecule mixing with a non-polar molecule that is carbon tetrachloride. So this is not going to be soluble as well. Not soluble. Also known as immiscible. Okay, pentane on the other hand. Pentane on the other hand, I'm going to have to make some room here. Let's see, I'm going to erase this guy. Okay. So I'm going to assume that you guys have this down already. Pentane on the other hand looks something like this. So each of these peaks indicate a carbon. So here's a carbon, 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 and carbon must have 4 bonds. So you have 3 hydrogens attached to these guys. In the middle, we have only 2. Okay, so looking at this, there's really not any difference in electronegativity. You have carbon here, carbon, carbon, carbon. That is a really similar similar amounts of hydrogen that are attached to it. So overall, we say that this is a non-polar molecule because the dipole moment is pretty well distributed. Everything's pointing sort of inward, and they're going to end up canceling everything out. So pentane is considered to be nonpolar. So when pentane is mixing with carbon tetrachloride, which is nonpolar as well, we have immiscible product, which means that it's completely dissolved. So it's immiscible product. It produces immiscible product and is therefore considered to be soluble. So it's best to, 1, draw the structures, 2, determine polarity, and based on the determined polarity, you can then decide soluble or is it not soluble. So X means not soluble. Sorry for bad handwriting. Alright. Nope, that's backwards. Let's go forward. Alright, some of the other factors that affect solubility are pressure and temperature. So pressure, surprisingly, actually has a very little effect on the solubilities of liquids and gas. However, when we're talking about gases, sorry about that, I'm gonna go back on that one. If you're talking about gases, they tend to become more soluble when the pressure of gases above the liquid increases. So imagine if you have a closed system like so, and you have your liquid here, and you have your gas molecules that are floating around in the vessel. The more gas molecules you input, so the greater the gas molecules increase, the number of gas molecules increase, some of these guys aren't going to have enough room to stay as gases. So what ends up happening is that some of these guys will then turn into partial liquid, making the gas molecules more soluble so that you have gas molecules that are dissolved in it. So it ends up increasing as you increase the pressure of the gas above the liquid. you're increasing the solubility of the gases into the liquid. Okay, temperature effect. Solubility of most solids increase with temperature. It's the same concept as if you have a cup of coffee. I love coffee. Here's coffee. It's my morning coffee. Let's say I put in a cube of sugar. Can't really see through it, but if I put in sugar, cold coffee, not going to dissolve very well. But if it's a really hot coffee, the immediate effect is that the sugar cube is going to dissolve completely very, very fast, right? And this is more of a common sense thing. So just think back to this example, coffee example, where do I want to, put the sugar cube in a cold coffee or hot coffee? So again, pressure has a little effect on liquids and solids, but for gases, the solubility increases as you increase the pressure. So that's the pressure that's being applied through inputting the gas molecules. No effect on liquids and solids, but gases become more soluble with the increase in pressure of the gas above the liquid increases. Temperature, think back to the coffee example, temperature increases, solubility of solids increase. Gases, on the other hand, always decrease in solubility because they want to evaporate more, right? So if you have water boiling, here's your, I'm going to use a darker color. Here's your pot of water. This is your handle, this flame here. You have, it's less likely that as you heat this water up, that the vapors are going to try to go back into a liquid form into your pot. No, as you increase the temperature, the waters are going to most likely increase, most likely to vaporize. So the likelihood of the gaseous particles that are floating above this pot coming back into liquid phase is very unlikely. So therefore we say the gases always decrease in solubility, so it's less likely to become part of the liquid body, the body of the liquid. Okay, I'm going to take a pause. It's about 10 minutes into the lecture, so let's pause this here. This then brings us to the vapor pressures of solution. I want to go ahead and say that I embedded this link here from Khan Academy. He does a fantastic job. I mean, just absolutely amazing job describing what the vapor pressure of solutions actually mean and what that means in terms of the likelihood of something that's going to be in either gas phase or liquid phase. I'm going to try to explain it here, but if you are confused, I would suggest that you visit Khan Academy for supplementary information, okay? Alright, but let's begin with the non-volatile solute that's being added. So when something is non-volatile, I'm sorry, I'm having issues saying that, but non-volatile means that it's not very likely for this guy to evaporate, right? So not likely to evaporate. So when this non-volatile solute is added to, say, a solution, a solvent, for instance, it lowers the vapor pressure of the solvent. So what that means is that when something is below a certain vapor pressure, if this is the threshold for something to become a vapor, it's called vapor pressure, right? If it's underneath that vapor pressure, then it's going to be either a solid or a gas. But now, if you happen to be above the vapor pressure, then you're most likely to have something that's more in the gas phase. So, when you add the non-volatile solute, it decreases the escaping tendency of the solvent molecule. So, for instance, let's say you have a pot that is boiling, and these are your water molecules, so to say. So when you only have water molecules, it's homogeneous water molecules throughout the pot, and you heat it up, these water molecules can just go anywhere and they can evaporate, right? However, let's say you add non-volatile volatile solute. Oh man, that's a terrible handwriting. I'm sorry. Look at that again. Let's say you add again here. Add non-volatile solute. Let's see you did that. Then what you end up having is you still have the same water molecules, homogeneous throughout the pot, right? But now you have these non-volatile solute that are also embedded in between the water molecules. Sometimes they're on top, sometimes they're on the bottom. But what ends up happening is that because of this interference of non-volatile solute, that means they're not very likely to evaporate, these solute get in the way of the water molecules' escape path. So you need to put in way more heat to give these guys more energy so that these guys can push these non-volatile solute outside so they can evaporate into a gaseous phase. Here, it was a direct path to the atmosphere. But here, they must get through all of these non-volatile solutes, so they require a lot more energy to finally escape out into the atmosphere. I know that was a very confusing diagram. Again, I really suggest that you guys visit Khan Academy for more information. But simply put, if something has a higher vapor pressure, then it's more likely to be in a gaseous phase. If it's got a low vapor pressure, not very likely to be in a vapor phase. Okay. Next up is Raoult's law. I'm actually going to leave this for part 3 as we are approaching nearly 20 minutes of lecture. So we're going to pick it up in part 3 of Unit 5 AP lesson plan. Thank you and have a great evening.